Hey everyone! So, here we are. Conservation of momentum is the topic for today, and I wanted to show you really quickly the three types of collisions that we are going to look at as a class. Now, when it comes to the law of conservation of momentum, it's one of the big four. One of the four things that is always conserved in the universe. The first, conservation of energy, conservation of linear momentum, which is what we're talking about right now, conservation of angular momentum, and conservation of a charge. So what I'd like you to do right now is write down what I have up here for the law of conservation of momentum. It says, in any collision, I think it could use a comma. In any collision, the vector sum of the linear momentum is the same before and after a collision. Let me highlight a few key words here. You have to remember that momentum is a vector. So we have to take into consideration its direction every time. Next, we are looking at the linear momentum. In this case, the momentum of an object that is traveling in a straight line. And lastly, we're going to look at it before and after. So, just to make sure everybody's up to speed, you guys remember the formula for momentum. If you don't admit it. It's the easiest formula in physics. It's something you probably have understood since you were a kid, where P is equal to mv. Those are all lowercase letters. And the units that we measure that in are simply kilogram, meters per second. Now, when we're talking about a collision, that implies that there are at least two different objects that are going to collide. So if we look at the momentum before and the momentum after, we need to take into consideration those two objects. So when I write out the law of conservation of momentum, I write it as P1 plus P2 initial equals P1 plus P2 final. Now, it's unfortunate that the letter P looks the same as an uppercase and a lowercase. But there it is. These are lowercase p's with the subscripts 1i, 2i, 1f, 2f. And there it is. Law of conservation of momentum. Now, if I were to expand upon this a little bit, I'm going to rewrite that as m1v1 initial plus m2v2 initial equals m1 v1 final plus m2 v2 final. It just rolls off the tongue after a little bit. Good. Write that down. Put a big fat rectangle around it, a couple stars. Make sure it stands out in your notes. When we are looking at a collision, momentum must be conserved. Good. Now, what I would like to do would be to take a look at that and the three different types of collisions where we can accurately predict what the motion of the object would be after the collision. And that's the key. The whole point in physics is that we can take a situation initially, something happens, and we can predict what's going to happen after. That's the beauty of it. So here, I've got two carts. Cart 1, cart 2. Now, cart 1 is a little bit tricky. I can store some energy in this spring that's located right in the front. And by compressing it, I can do work to the spring, and now the system has energy. You know what it doesn't have right now? Any momentum. Yeah, that's right. So I'm going to take that cart right there and place it. What's its momentum? Yeah, good. What is it? 0. That's right. Now, if I take my other card and carefully place it beside it, what's the momentum of the system? Still 0. She's got it. That's right. So, let's draw a picture. The first type of collision that we are going to look at is ones where it starts with no momentum. Number 1 is when they start at rest. Now, I know you're thinking, huh? What's this have to do with a collision? Well, a classic case of starting with no momentum is when you fire off a cannon or you fire off a gun. When you fire off that gun, the bullet's going to have what traveling to the right? Yeah, momentum, very good. But what about the gun itself? Of course, it also has momentum traveling in the opposite direction. The total momentum of the system has to be conserved. So right here, if it starts at rest, let's draw a picture. I'm going to have cart number 1 and cart number 2, both sitting at rest. They have equal masses. And then the spring is released. I'm going to have cart number 1 traveling to the left, whoop, with the velocity 1 final. Ooh, that looks pretty small. I don't know if you can see it out there. Cart number 2 is going to be traveling to the right, V2 final. But let me ask you this. How can momentum be conserved if it's not starting with any? Well, let's take a look. Ready? So let me hit the trigger. And we're going to start with no momentum, and afterwards, we did have momentum, didn't we? Both carts had momentum. Yeah. Somebody just got it out there. Good. Good. Now remember that momentum is a vector, right? So what can you tell me about the momentum of cart number 1? Positive or negative? That's right. It's going to be negative. Cart number 2? Positive. So the sum of the momentum before is 0. The sum of the momentum after, it's still 0. Good. All right. I can look at a situation where maybe this time we have what's launching the second object have much more mass. Now, momentum is still going to be conserved. So after I release that energy, in this case in the form of a spring, if it was a cannon, it would be gunpowder. The velocity of the first cart is going to be less in the negative direction, obviously, than cart 2, which has less mass. However, what can you tell me about their momentums? Yeah, oddly enough, their momentums are still equal. Cool. Let's take a look at the math on that. Wait, the math can't get any easier. Let's try it. So if I go ahead and write out my formula, M1V1 initial plus M2V2 initial equals M1V1 final plus M2V2 final. But like I said, we were starting at rest, so the left-hand side of my equation, each go to 0. And maybe to clean this up, I'm going to subtract this over, and I'm going to have negative M1V1 final equals M2V2 final. Ding, ding, ding. Piece of cake, huh? Yeah. It's also a classic type of problem when both objects start. Later, momentum must still be conserved. So what's the second type of collision? That's a good question. This is a type of collision that we call an inelastic collision. And yes, I pronounce that funny because I don't want you to get it confused with another type of collision that we'll talk about in just a moment. But in an inelastic collision, momentum is always conserved, but the kinetic energy is lost. That is the definition of an inelastic collision. The momentum of the system is conserved. However, the kinetic energy is lost. It doesn't mean that energy is lost. Just energy in the form of kinetic energy is transformed into another form, usually heat and sound. So kinetic energy is lost. The simplest one of these problems occurs when two objects stick together. So if I take two carts, and these have Velcro ends on them, and I start one cart at rest and start my other cart moving, and I send it forward with some positive momentum. At the point of collision, the two pieces of Velcro are going to stick together, and what we're going to have is they're going to travel off to the right. Now, the thing is, the total momentum of the system must be conserved. So before I do that, let's draw a picture. I'm going to draw my cart. Cart number 1 coming in with a velocity v1 initial, colliding with cart 2, which is at rest. Yeah, this is easy stuff. Easy stuff for people like you guys. Then a collision happens. Now, this is what I love about conservation of momentum. It's actually just a giant pictogram. There's the collision. And what we have after is cart 1 and 2 stuck together. Now watch what happens with the math. It's so nice and easy. Let me finish my picture first, though. V2F. Oh. Let's come back to that in just a second. When I do the math out, let's look. I've got M1 V1 initial plus M2 V2 initial. I know cart 2 is at rest in this case, but it won't always be. Equals, ready? M1 V final plus M2 V final. Because if they're stuck together, which one's traveling faster? Yeah, of course. Neither, right? Yeah, neither. Neither one's traveling faster. They're traveling at the same speed. So that's going to become VF. Now, Hannah sees it. What can I do to those VFs right there? No, I can factor them. Don't they teach you anything in 6th grade? I can factor out the VF, and it becomes VF M1 plus M2. Now, I know you're a physics student who's at this point, you're just having trouble with the stupid subscripts. But relax, as a physics teacher, here's what I see. And this is what's so beautiful about it. When the two objects are stuck together after the collision, and the final velocity is the same for each object, there's only one unknown. If I know the initial situation, then a collision occurs and they stick together, I can accurately predict what the velocity after the collision will be. And that's a powerful thing. And it's also actually fairly easy too. Another good reason to like it. So here I'm going to have a collision come in, and what you would expect to see happen, happens. Momentum is conserved because the cart slowed down. Pretty easy, huh? But how do we know that kinetic energy was lost? Well, let's try another example. I could have positive momentum, yeah? Give them both a push. Then after the collision, I still have positive momentum, and they're equal. But what about if I do this? If I send this one to the right, has positive momentum and kinetic energy, right? Positive kinetic energy. Right here, negative momentum. But positive kinetic energy, right? Because kinetic energy is a scalar, it doesn't have direction. Kinetic energy is going to be positive. Positive momentum, negative momentum at the point of collision. Yeah. How much momentum does it have now? That's right, the same as before, because momentum is conserved. Before we had no momentum for the system before the collision, and now we have no momentum. But what about the kinetic energy? Was the kinetic energy conserved, Hannah? No, it was not. The kinetic energy was clearly lost. 6th graders. Let's take a look at that again. Oh! All right, so here we are. Third type of collision. This is actually the one that is the most interesting and can be beautifully illustrated by our Newton's cradle. Oh, but I can't lead with that. Then you guys won't pay any attention. So I'm going to put that aside, and we'll talk about that at the end. The third type of collision. that we're going to study and quantify are collisions called elastic collisions. The previous one was inelastic. This is elastic. And yes, I try to over-enunciate, but it's an elastic collision. Now, the thing about elastic collisions is that both momentum and kinetic energy, oh, I'm going to put that as an and, excuse me, and the kinetic energy are conserved. Now, elastic collisions are what you see, let's see, a decent example. If you're at the pool hall, billiards balls undergo close to elastic collisions. If you're bowling, the bowling ball hitting the pin, pretty close to a perfectly elastic collision. In science, in the real world, where it actually matters, atoms undergo perfectly elastic collisions. When we say atoms in a gas are colliding right here in this room right now, there's atoms in between me and the camera that are constantly colliding as they move with a velocity relative to their temperature. Those are having perfectly elastic collisions. So, what's it look like? Well, if I take my carts here, and I take one of them and flip it around. Oh, there we go. Now, I have magnets in the end of these carts, and I should be able to apply that force over a distance without them touching. Therefore, it's not going to turn any of its energy into heat or sound. So, momentum and kinetic energy must be conserved. Now, I have equal masses here, so I'm going to take cart number 1, give it a push, and what's going to happen? In the collision, the other cart carried away both the momentum and the kinetic energy, equal to what we started with. So if I have two equal masses that collide elastically, that's what we're going to see. Does this remind you of anything? Yeah, I know it does. Hold your horses. But things are different if we have different masses. So if I make cart 1 have more mass now in this collision, the momentum and the kinetic energy still must be conserved. So because this object is lighter, has less mass, after the collision, it's actually going to travel at a much greater velocity. And this larger mass is actually going to continue on. Now we're going to demonstrate this big time with bowling balls in class. And that'll be fun. But for now, let's just take a look at that. If I have a smaller mass collide with the larger mass, I guess I could do it this way. What do you think is going to happen? Yeah. Is momentum conserved? Is momentum conserved? Yeah. Yes, it is. Even a 6th grader knows that. Pay attention. Good. Yeah. Momentum's conserved. You getting tired of this? Then draw a picture. Now, if I show that cart coming in, draw it. Draw it. I can feel you drifting. Come back. Cart number 1 with V1 initial colliding with cart number 2 with V2 initial. Now, I got things going left and right. Whenever that happens, I better include a positive arrow to indicate the direction. That's critical. But after the collision, what's going to happen? Total momentum and kinetic energy must be conserved. So what I'm going to have is cart number 1 traveling to the left and cart number 2 traveling to the right. Now, let's see what that looks like mathematically. Ready? If I use my law of conservation of momentum, M1 V1 initial plus M2 V2 initial equals M1 V1 final plus M2 V2 final. I know. Aren't you surprised when that just rolls off my tongue every time? Yet I stutter on simple words. Now, the thing about this is if I know the before you would assume I can calculate the after. And I can. However, I do have two unknowns here, don't I? And if the masses are not exactly equal, well, the math gets a little trickier. However, with two unknowns, if I have another relationship, I can solve it up. Now, look behind me. It says both momentum and kinetic energy are conserved. So I'm going to go ahead and write out the kinetic energy of the system initially. 1/2 m1v 1 initial squared. Now we're doing some physics. Look at all those subscripts. Plus 1/2 m2v2 initial squared equals 1/2 m1v1 final squared. Yeah. 1/2 m2v2 final squared. Yeah. I know, relax. I know I could cross off the 1/2. I understand that. In fact, it was that crossing off that 1/2 that made it so that Newton actually never understood the concept of kinetic energy. So hold your horses. But when I look at this, I'll still know my before and my after. I have two unknowns and two equations. And what do we call that? What do we call that in math, Hannah? That's right. They have studied that in 6th grade. A system of equations. Does that sound familiar? Yeah. No, it doesn't. They just learned that like last year. The kids that are in this class right now. You've done system of equations? She's lying. She's lying. Don't believe it. All right, you guys. Now, I think that's it. Anything brilliant here? No. Did we get through some material? Yeah. So you know what we're going to end with? We're going to end with Newton's cradle. That is the appropriate physics name. We don't call it anything else. A Newton's cradle. Here I start with one ball. It has potential energy, turns into kinetic, and then has a collision. But we are going to assume that they're perfectly elastic collisions. So both momentum and kinetic energy are conserved. Now you can see a little jiggle in there. I'm not some high-priced executive who has a fancy one of these. I have one that students have been messing with forever. What happens when I take two of them and pull them back? How many are going to go up on the other side? Hannah says 2. Oh, and look at that. Nice work, Hannah. What if I do 3? How many go up on the other side? 3. She called it. What if I do this? Then I have a horse. All right, I'm going to call it right there. Whew. Thanks for hanging in there. Conservation of linear momentum. There it is. I usually don't bow, Hannah. I just felt like since you were here live, I had to bow.